Yesterday we talked about the energy changes that happen in chemical reactions, and we saw the graph that has the activation energy, but they also happen with physical processes, and what I mean by that is like phase changes. So the graph we're going to look at is called a heating curve, and it looks like a staircase. And the whole point about this heating curve is that the temperature changes as it's heating, but not during a phase change. So what happens here is you start with a solid that's really cold, and you can heat that solid up until it reaches the melting point, which happens right here at letter B. At this temperature, right here at B, you still have 100% solid, but it's at the melting point. So if you keep putting energy into it, what's going to happen is it's going to turn into a liquid. And the crazy part about this is, if you have an ice cube on your hand and it's melting, it's tempting to think that that ice cube is getting hotter and hotter. It's actually not. The energy is going into the ice cube, but it's not increasing the temperature. It's actually breaking the bonds and causing it to melt until at letter C you have 100% liquid. So notice that the temperature did not change during this portion right here. It stayed flat, but you started with 100% solid and you ended with 100% liquid. And once all the liquid molecules have turned into liquid, then you can start to heat it. So once all the solid molecules have turned into liquid, then you can heat it some more. So what's happening here is that the liquid is getting hotter and hotter, the temperature is going up, until boom, right here at letter D is where it reaches the boiling point. And notice that again the temperature levels off. It's tempting to think that the longer you boil water, the hotter the water gets, but it actually stays the same exact temperature until every single water particle has become gas. So this is called vaporization. And then here at letter E, once you have 100% gas, then you can heat the gas up even more. So notice that on the diagonal lines you have one state of matter, and on the flat lines it's a phase change. So the important part for today is that temperature does not change during a phase change. And the reason is because all the energy that you're putting into it is breaking the bonds, it's not speeding up the particles. And remember, the speed of the particles is kind of like the temperature. If we talk about it in terms of energy, we've talked about the temperature is average kinetic energy. So anytime the temperature changes, you have a change in kinetic energy. And two more things I forgot. Boiling point, notice, is way up here at the first flat line, and melting point is down here at the second flat line. Make sure you label that on your graph. So temperature changes are kinetic energy. So notice that on the diagonal lines you have a change in kinetic energy. The other type of energy is called potential. And that means stored energy, which has to do with the chemical bonds. So anytime you're breaking bonds, you're going to change the potential energy. And notice that that happens during phase changes. So you could take this exact graph and turn it around if you're cooling something. So this one's called a heating curve. A cooling curve is the same, except you're starting at a hot temperature and going down to a cold one. So notice that we started as a gas, and you're going to cool the gas until you reach a certain point. This is the condensation point. And then at this point it's going to start to turn to a liquid, but notice the temperature stays the same. Once every single gas particle has become a liquid, then you can cool the liquid even more. So cool it until it reaches this point, which is the freezing point. And at this point it's going to start to turn into a solid, but notice the temperature doesn't change. And then once every single particle is solid ice, then you can cool the solid even more. So what you'll need to know is whether the phase changes are endothermic or exothermic. And the endothermic ones for me are a little bit easier, so let's do those first. What I would suggest is if you just list SLG, solid liquid gas, and let's do the first one from solid to liquid. So draw a little arching arrow that goes from S to L. If I have an ice cube and I want to turn it into liquid water, I know that I have to put heat into that, which means it's going to be endothermic. So that one makes sense in my head. Same thing for liquid to gas. If you draw an arrow from the L to the G, draw a little arching arrow. Liquid to gas, anytime I boil water, I know that I put it on the stove, I don't put it in the refrigerator. So that tells me that it's endothermic because I have to put heat into it. And same thing for solid to gas. So anytime you have an arrow going in the right direction, it's going to be endothermic. If you go backwards, that's where it's a little weird for me. So if you go from liquid to solid, in order to make those liquid particles become solid, you have to actually remove energy from those particles because they're going a little bit faster as a liquid and they're flowing. And to get them to be a solid, you have to slow them down and get them to stick together so they're just vibrating. So you have to remove some of their energy, and that's exothermic, when energy is coming out. Same thing for gas to liquid. If you want to slow those gas particles down and get them to stick together, you have to remove energy. So if you draw an arrow from G to L and draw an arrow from L to S, those are all exothermic, and the same thing for gas to solid. So basically, anytime you go to the right on this picture, it's endothermic. If you go to the left, it's exothermic. So melting is endo, freezing is exo, boiling is endo, you put heat into it, and then condensation is exothermic. And if you blank out on the test, I would just sketch out this little picture, SLG, draw your arrows, and know that to the right is endo, to the left is exo. The next definition is called specific heat, and it's kind of a long definition. The key words there are 1 gram and 1 degree Celsius. So once you write this out, I want you to circle 1 gram and 1 degree Celsius. This is the amount of energy it takes to increase the temperature of 1 gram of something by 1 degree Celsius. So for instance, water has a very high specific heat, which is why it takes a lot of energy to make it turn into a different temperature, to make it change temperature. Which is why on a really hot day, if you leave a water bottle in the car and go into the mall for several hours and come back, your car and your seatbelt could be really hot, but if you open the water bottle, you could probably still drink the water. It's not going to be boiling water yet. And that's because it takes so much more energy to heat water up. And these are in your reference tables. So if you take a look at the first page of your chemistry reference tables, towards the bottom there's a chart, and you'll notice that one of the columns says specific heat. So if you ever need the specific heat of a metal, you're going to look on that bottom part there. And then about halfway down you'll see where it says specific heat of water, and there's 3 numbers. There's 2.02, 2.05, and 4.18. Those are the specific heats of water, but it depends on what state of matter it is. So you have to be careful. If you have solid ice, you want to choose the 2.05. So what we're going to do is calculate the amount of heat involved in different things. And remember I said you can't measure heat. You can't go to the lab bench and actually measure the heat because heat is a transfer of energy. But what you can do is measure the temperature and use this equation to calculate the heat. Sometimes we call it the MCAT equation because it looks kind of like MCAT. So if I ever say that, that's what I'm talking about. And for science, you kind of have to get out of your head the positive and negative thing from math. In math, positive means above 0 and negative means below 0, but in science, it just tells you direction. So a positive Q tells you that heat is going into the system, a negative Q tells you heat is going out. So this positive and this negative has nothing to do with the value of the number, it just tells you the direction of the heat flow, because remember, heat is a transfer of energy. So for this equation, Q stands for heat, and that's going to be either in joules or calories. M is the mass, and that's in unit of grams. C is the specific heat, and it has a really big unit. This is not an equation, this is the unit for specific heat. It's joules per gram degree Celsius. And notice since this has Celsius in the unit, your temperature for this chapter is also going to be Celsius, so don't turn it into Kelvin this time. And then delta means change, so delta T is a change in temperature, and it's really important that you do the final temperature minus the initial temperature. Always do T final minus T initial. If you set it up this way, you'll always get the correct sign, whether it's positive or negative. Make sure you do final minus initial. The next vocabulary word is kind of similar. Oh, sorry, let's write this down first. So temperature change doesn't happen during a phase change. So therefore we can't use this equation during the flat lines. On that staircase graph that we did at the beginning, anytime you have a flat line, meaning temperature is not changing, we cannot use the MCAT equation. And that's because delta T would just be 0, which would make Q 0. So if it's a phase change, there's a different equation that we use. If it's vaporization, we're going to use the heat of vaporization. And the key word there is just 1 gram liquid to gas. It's the amount of energy it takes for 1 gram of liquid to turn into a gas. And this one kind of makes sense because vaporization obviously is liquid to gas, so you can picture in your head that it's going to be liquid and gas. You also use this if you're going backwards, so the amount of energy released if you go from gas to liquid. And this is our equation. HV stands for heat of vaporization, and if you look at your reference packet about halfway down on the first page, it says heat of vaporization of water, and it should say 2260. So you don't have to memorize that. We're just going to use water a lot in this class, so that way you'll know where it is. And the last one is if you have solid to liquid or liquid to solid. So heat of fusion is the same thing. It's 1 gram, but this time you're either going solid to liquid or liquid to solid. So vaporization is easy because I see the word vapor, so I know it has to do with a gas. Fusion's a little bit harder because I don't see anything in there that helps me, so the way I remember it is that there's an S in there for solid, and that way you know that it's a solid is involved with this one. And it's the same equation. Heat of fusion of water, again, is about halfway down on that first page. So let's talk about how to calculate these. If you have the staircase graph in front of you, it'll help you. So for the first question, it says we have 200 grams of liquid. We're going from 30 to 90. So if you look at your graph, water freezes at 0 degrees. So the first flat line is at 0, and the top flat line is at 100. So 30 to 90, we're just staying within the liquid range. So we're going to use the MCAT equation. You plug in your mass. This is the specific heat of water that's on the first page of your reference tables. Just make sure you choose the liquid one. And then for temperature, be really careful. Make sure you do final minus initial. It's tempting to say 30 minus 90, but you always want to flip it around. And notice that this value is positive, which makes sense because of this phrase right here where it says heat is added. Anytime it's endothermic, you're going to get a positive joules. For the next one, it says heat is being absorbed, so again, we should get positive. This time we have ice, and we're going from -10 up to -5. So if you look back at your graph, the first flat line is at 0, so we're not going to even get up to a phase change. So we're going to use MCAT again. Plug in your mass. You have a different specific heat because now it's solid ice, so be careful with that water specific heat. Make sure you choose the right state of matter. And then again, be careful with your negatives. You want to do final, which is -5, minus the initial, which is -10. So you do -5 minus a -10. And notice that it's positive, which makes sense because heat is being absorbed. For the next one, I tried to help you out by giving you a hint. Notice that I underlined the word released. That means that heat is going out of it. So in this case, it's going to be exothermic, and your final answer should be negative. So if you look at the temperatures, we're going from 160 to 115. So if you look back at your graph, notice that we're going to stay in that gas area. We're never going to get down to that flat line. So again, we can use the MCAT equation. Plug in your mass. This time we have steam, which is the same thing as vapor. Notice that I did final minus initial, which is how I got a negative number there. And that negative makes sense because heat is being released. It doesn't mean we have less than 0 joules. We have 44,545 joules. The negative just means that it's being released. For the next one, it says we're going to turn ice into liquid. So this time we're doing a phase change. Notice that they gave us a temperature, but we're not actually going to use it because during a phase change the temperature doesn't change at all. So they're just telling us the temperature when this happens, but it's not important in the question. So for ice to liquid, we're going to use Q equals M times HF. All you have to do is plug in your mass. This number came from your reference tables. It's on the first page about halfway down. And just check and make sure your answer makes sense. We have a positive Q, which makes sense because it's being absorbed. And the last one, again, notice released, so we need to watch for that. We have 90 grams of water vapor, turning it into liquid water. So again, it's a phase change. They told us the temperature, but the temperature's not changing because it's a phase change. So we're not even going to use the temperature. All you have to do is the mass times the heat of vaporization, which is in your reference packet. The problem is, anytime you use the phase change equations, you'll always get a positive number, so you have to ask yourself, should it be negative? And it should be, because heat is being released, so you have to physically draw the negative sign on there, even though you didn't calculate it. So the last thing you want to do for all of these questions is see if it should be positive or negative, and just make sure your answer matches. And if you try some on worksheets 2 and 3 in your packet, that should help you. Worksheets 2 and 3. And that's all for today.